Hi there. The Bohr atomic model was able to explain the hydrogen spectrum. However, it was not successful in fully describing the spectrum of heavier atoms. Thus, a new theory was established around the year 1920s. This is the quantum mechanics. This is the outline of this video lecture. We now establish the duality of light, that it shows the wave properties through interference, diffraction, and refraction. Also, it has particle properties that includes the photoelectric effect and Compton scattering. With this, Louis de Broglie in 1924 said that a particle, such as an electron, can also act like a wave. So the pronunciation of this is de Broglie and not de Broglie, which is also my usual pronunciation. The momentum of a photon can be described as follows. Using the same logic, Louis de Broglie proposed that a particle of mass m moving with a momentum p has an associated wavelength called the de Broglie wavelength, as shown. So this is the de Broglie wavelength, which is equal to h, or Planck's constant, over the momentum p. We also have this expression for our momentum p, as shown. And if that is the case, then it should be true. Also that, let's say, a basketball. For a large objects, lambda, the wavelength is very small, so that the wave properties are not observed in a basketball, as an example. So now we have this illustration. We have a beam of particles, let's say an electron or a group of electron, can be diffracted and can undergo interference, as shown. When a beam of electrons was introduced at two parallel slits, we will be able to produce the same pattern as for the interference of light. As more electrons hit the screen, the light and dark bands becomes more prominent. Now let us go to the Schrodinger's equation. Let us define first a certain transverse displacement determined by this wave equation. So this is our transverse displacement function, and your wave equation, this is the second partial derivative of y with respect to time. And this is the speed v. Then we have here the partial derivative of y with respect to the displacement x. This displacement function can be a standing wave, as expressed here. It's like the one observed in a musical instrument or a vibrating string of a musical instrument. So using the wave equation that we have shown previously, we will be able to get this equation after the substitution. Then rewriting the equation, we have this differential equation. We can re-express the angular frequency here, omega, and we can rewrite omega over v into 2 pi over lambda, the wavelength. In addition, we can express our wavelength, the lambda, using the de Broglie wavelength. So that's equal to h over t. And therefore, the omega over v is equal to p over h bar, as shown, wherein h bar is our reduced Planck's constant. This is our original differential equation for this function psi. So, but we express omega over v, which is equal to p over h bar, and therefore, we now have this form of our differential equation. If the potential energy of our particle is equal to ux, or u as a function of x, then we can rewrite the total energy as follows. So E is equal to the kinetic energy of that particle plus the potential energy, and we can get the expression for our momentum squared, p squared, which is equal to this. So thus, our differential equation is now equal, or now have this form. Therefore, this is our wave equation in one dimension. This is not a thorough derivation of the wave equation. You can get a more detailed derivation in a quantum mechanics reference. Here we have the wave function psi as a function of x, and for a given state wherein the energy E is said to be constant with respect to time. And this is called a stationary state. In mechanics of vibrating violin string fixed at both ends, we have definite vibration frequencies or those harmonics. In quantum mechanics, on the other hand, a Schrodinger's equation with boundary conditions will result into discrete values of energies. We can have this potential here of an electron in hydrogen atom to find its solution and energy levels. For the wave function, the square of the absolute value of the wave function can be interpreted as the probability of finding a particle between x and x plus this infinitesimal dx. This can be also interpreted as the probability density of measuring a particle being detected at a given place or a given momentum. The integral of this over all the system's degrees of freedom should be equal to 1 since the particle has to be found somewhere. And this is called the normalization condition. So thus, our psi, the wave function, is said to be normalized. The average or the expectation value of any physical property fx can be calculated if the wave function is known. This is written as this, the one shown here, and if the function f here is equal to, let's say, a position of our particle x, we can get the average value of our position x. Let us now consider a particle with mass m, free to move in a small space surrounded by these impenetrable barriers with the width L. So let's say this is 0, x is equal to 0, and this is x is equal to L. The potential energy is 0 inside the box. Outside the box or outside this well, the potential energy is infinite. Thus, no particle is present outside this well. We will define the boundary conditions as shown. At x is equal to 0 and at x is equal to L, our wave function is equal to 0. Thus, the Schrodinger equation will have this form as shown here, where k squared is equal to 2me over h bar squared. The solution of this differential equation is but given by the boundary condition. And this is the general solution for this differential equation. And following our boundary conditions, we can get that dB, the constant b here, is equal to 0. Thus, we have this psi of x, which is equal to a sine kx. Since when x is equal to L, the wave function is equal to 0 based on our boundary condition. So thus, the solution for this is psi x is equal to a sine n pi x over L. The standing waves will have a wavelength of 2L over n, and the particle momentum can be expressed as h over lambda, which is equal to n h over 2L. So it is also quantized. Therefore, the energy is quantized as shown in this equation. We can express the energy E sub n is equal to h bar or h squared over 8ml squared n squared, wherein n is equal to 1, 2, 3 above. The n here is an integer called the quantum number. Now we use this to label a state. Now, if we want to get the value of the constant A for our wave function, we need to apply the normalization condition as shown. So we will get the value of the constant A as shown. So A here is equal to the square root of 2 over L after we have done this integration, the normalization condition. And therefore, we can rewrite our wave function psi of x, which is equal to the square root of 2L sine and pi x over L. In classical physics, the particle can be detected anywhere in the box with equal probability, shown here in box A. On the other hand, in quantum mechanics, the probability density for finding a particle at a given position is derived from the wave function. Okay, now let us discuss particle in a finite well. Let us now have a finite potential well with a finite depth U shown between 0 to L. The potential energy is 0 at the bottom of the well. We have three regions, region 1, region 2, and region 3. At region 2, the Schrodinger equation is equal to this, wherein k squared is equal to 2me over h bar. Same with our discussion previously, the solution for this is equal to a constant c times sine kx. Note that for this finite well, we cannot impose that the wave function is 0 at the barrier or wall. Let's now go to regions 1 and 3. At regions 1 and 3, the potential is greater than E. Thus, we have this Schrodinger equation. Given that k squared is positive, the solution of this differential equation can be written using our exponential functions. We impose that the wave function will approach 0 if x approaches positive and negative infinity. Thus, the solution for this wave function at regions 1 and regions 3 are the following. For region 1, we have this exponentially increasing, and for region 3, we have an exponentially decaying wave function. The solution for a particle in a finite well shows that when a free particle, say we have a free particle here, encounters a certain potential barrier with height u is greater than e, classically that particle requires enough potential energy to cross this barrier. However, when we solve the Schrodinger equation, we find an exponential decay for the wave function present within this barrier region. Thus, a finite probability that the particle will tunnel through this barrier. And this finite probability, this is observed in alpha particle emission and in tunnel diode. The Heisenberg uncertainty principle discusses a fundamental precision limit with which the value of certain physical quantities of a particle can be predicted from the initial condition. We have here first the position, then we have the momentum for one-dimensional along the x. It should be greater than our h bar, the reduced Planck's constant. Can also be the uncertainty in the energy and the time of a system in a given state. One example is, let's say, a free electron with a wave function as shown uh, of this is a sine spread in space. It has a defined wavelength and momentum, but the uncertainty in its position is infinite. Or now let's have a particle localized in a box, or a particle in a box. A particle is located somewhere in a range. So the wave function here is a wave pocket. Then a particle is located somewhere in this range, but it is a superposition of different wavelengths. Thus, we are uncertain about its momentum. For the summary, electrons and other types of particles have wave properties. The wave function of a particle contains the information about that particle. The Schrodinger equation is a linear partial differential equation that describes the wave functions of a quantum mechanical system. Last, Heisenberg uncertainty principle shows the limit in the measurement precision for certain physical quantities of a particle. Hi! If you have learned something in this video and you like my content, please consider subscribing my YouTube channel, GT Academia. See you in the next video.